This short video is to help you with calculations involving energy, frequency, and wavelength in the electromagnetic spectrum. Just a brief review of what we've already talked about with regard to the electromagnetic spectrum. In addition to the visible spectrum, we have the entire spectrum, which goes from one extreme of gamma radiation at one end to radio waves at the other end. Gamma radiation being high in energy, high in frequency, but very short wavelength. The flip side of that is radio waves, which are long wavelengths but low in energy and frequency. As you can tell from this relationship, energy and frequency are directly related. Energy and wavelength, as well as energy and frequency, are inversely related. That has to do with the concept of a wavelength and frequency and energy. I'm not going to go into that at this point in time, but just to review again the difference between direct and inverse, I have a little diagram. Here's the equation: energy equals Planck's constant, h, times frequency. And if you were to solve for h, the constant, you would have energy over frequency, and that is how we would plot an equation for a line: rise over run, y over x. The other relationship, wavelength times frequency equals c, which is the speed of light. If you solve for the constant, well, it already is solved for the constant. It's not going to give you a line, it's going to give you a curve. The nature of this podcast, however, is to talk about light and the way in which we can work with light. And there are two ways that we can view light, both as a wave and do calculations using the speed of light, c, equals wavelength times frequency, or we can consider light as a particle, energy equals Planck's constant times frequency. The calculations that I'm going to show you today involve these two equations. The constants you don't have to memorize, but I have them in the table for your use. They're also in your textbook. Speed of light, c, 3.0 times 10 to the 8th meters per second, whereas Planck's constant, h, 6.63 times 10 to the minus 34 joules seconds. Now, one thing that's important to review is how you use your calculator. Remember, we use the E button on the calculator for scientific notation. So if you've forgotten how to do that, you might need to go back to the first month of the year and review your notes on that. I'm not going to take the time to do that right now. Frequency is interesting in that there's many different units, but the unit that we use most often is 1 over seconds, or seconds to the minus 1. Hertz is the unit that's often used when we're thinking about broadcasting frequency, so perhaps you have seen or heard of that before. So a broadcast frequency is different whether we're talking about FM or AM radio. FM is broadcast in megahertz, capital M here, and AM radio is in kilohertz. That's not really that important for us today. Let's focus our attention on performing a calculation with a given speed of light that is in the visible spectrum. So calculate the energy of it's not in the visible spectrum, it's ultraviolet light. It has a wavelength of 125. Well, that makes sense. I know that violet or visible light is in the 400 to 700 nanometers. Since this is lower wavelength, it would be of shorter wavelength than violet light, and so that makes sense that it would be in the ultraviolet region. Notice the wavelength is in nanometers. Since our constants have units of meters, then we can't use units of nanometers. So the first step is to convert nanometers to meters. The second step will be to calculate frequency using the equation given here, and then finally taking the frequency that we calculate and plug it into the final equation. So that's what we're going to do here in the next slide. So let's cover up some of this so we're not distracted. So the first step is remembering how to convert between nanometers and meters. So we have 1 meter equals 10 to the 9th nanometers. 1 meter, 10 to the 9th nanometers. So if we have that equality and our given is 125 nanometers, then we can put our given over 1 and multiply by a ratio, as shown. Now, pretty standard. Dimensional analysis, canceling the units just like we've done. Now the next step will be to, given the wavelength, we want to calculate the frequency. Once we calculate the frequency, then we're going to calculate the energy. Why don't you pause the slide? If you have the constants, if you have the frequency, or excuse me, the wavelength, then plug in the constant, plug in the wavelength, and see if you can come up with the correct answer for frequency before I go on. Have you paused the slide? I'm back on. I'm ready to show you the answer. Calculate the frequency. I'm going to plug in the values. I'm going to solve for frequency. And when I do that, I isolate the variable, meters will cancel, and I have a value of 2.4 times 10 to the 15th. Now, if your frequency is off, it's probably because, if your number is correct here, but your exponent is off, then it's probably incorrect calculator use. So make sure that you go back over your notes and double check that you're using the double E button on your calculator properly. All right, now we've got the frequency. The last step, again, let's go back to that slide. Energy equals Planck's constant times frequency. We've got the frequency. All we need to do is plug in the Planck's constant to calculate the energy. Pause the slide here and see if you can calculate an answer. Once again, testing yourself to be sure that you can properly use your calculator. And the answer is 1.59 times 10 to the minus 8 joules. Now, if you were going to calculate, instead of energy, if you were given energy and going to calculate frequency and wavelength, they're the same equations, you're just going the opposite direction. I hope this podcast helps, and good luck with those calculations. I know some of you said you were struggling with that. Good luck.